Machine learning is becoming a key tool for science. NASA's Heliophysics division has been learning by doing, pushing the limits of what's possible in ML through its 5-year partnership with the Frontier Development Lab to better understand our star and predict its interactions with Earth. This talk is a snapshot in time of what's possible when ML is applied to science domains with massive heterogeneous datasets, helping both to safeguard and improve life on Earth, unlock the secrets of the universe, and better understand habitability. I will showcase cutting-edge applications of ML to the physical sciences through the lens of heliophysics, providing a unique view of ML's ability as a tool for exploration and discovery. In addition to the NASA missions used in research, there are additional missions also operated by NOAA used for space weather forecasting. This video shows NASA and NOAA heliophysics fleet from the near-Earth satellites out to the inner solar system. The satellite orbits are color-coded for their observing program. Magenta is thermosphere, ionosphere, mesosphere observations, yellow solar observations and imagery, cyan geospace and magnetosphere, violet heliospheric observations. This visualization presents orbits of the current heliophysics satellites covering the space near Earth out to the Sun-Earth Lagrange point L1, and finally a view of the current missions operating in the inner solar system, the newest of them being Parker Solar Probe and Solar Orbiter collaboration with European Space Agency. There is much to do. The good news is that machine learning tools are maturing quickly. Integration of physics and explainability is enabling AI to become a powerful tool for discovery. Some of the examples I will go through. SuperResolve is an example of workflow for optimization, which is cost and time savings and results in enhanced data products. 50 years of solar magnetic field data. Or think of creating virtual instrument is an example of forecasting and prediction of extreme ultraviolet irradiance, enabling virtualization of SDO instruments. Or make forecasts is an example of applying decision intelligence with rapid assessment, improved strategic decisions for prediction of GNSS GPS disruption 1 hour in advance. Or extract insight from noise is an example of anomaly detection, mapping star spots hidden in test data. This challenge was to create a homogeneous set of magnetograms. Numerous observatories have monitored the sun's magnetic field over the last 50 years with high level of inhomogeneities, reducing their effective value for understanding long-term variability. The question was, can we apply machine learning for calibration and super resolution? And that's kind of what we went about. Can we calibrate and super resolve historical observations of the solar magnetic field, taking into account the inhomogeneities such as resolution, noise, and saturation levels? The ML pipeline cross-calibrated and upsampled data from older instruments like SOHO, Michelson Doppler Imager, MDI, to create a homogeneous observational baseline with newer Solar Dynamics Observatory HMI, which is helioseismic magnetic imager, thus creating a super resolved image of the sun's solar magnetic field upscaled to contemporary instrument. And to this, of course, we added all the ground-based data like GONG. By using a prepared air-ready SDO dataset, this challenge aimed to transfer HMI data into extreme ultraviolet images. Using 4 years of 7 cotemporal EUV channels from SDO AIA, the team successfully developed an auto-calibration model for EUV images from AIA. This technique can be adapted to other imaging or spectral instruments operating at other wavelengths. Top row, an overview of the degradation of 304 channel. It's recovered images and the architecture used, as you can see. And then in the lower panel, the bottom row, comparison of real 211 angstrom channel and synthetic 211 channel. So this is basically expanding capabilities of Solar Dynamics Observatory. The results are the team devised a way for solar extreme ultraviolet telescopes to self-calibrate, improving our capability to monitor space weather, removing the need to perhaps fly rocket flights under these missions for calibration. Furthermore, the team created a synthetic telescope to image the sun's corona. These techniques enhance the scientific return of space missions and paves the way for an autonomous space weather constellation in future. Measurement of solar spectral irradiance is needed for satellite orbit boost planning due to satellite drag and whole host of other effects that spectral irradiance plays on our atmosphere. Currently, this is difficult because one of the primary sensors on Eve SDO, called the MEGS-A module, stopped functioning in 2014, which was collecting this data. So the question was again, can we predict solar spectral irradiance from SDO AIA observations only? The SDO AIA UV imager co-observed with MEGS-A from 2011 to 2014, and can we use this data overlap to train a deep learning model to virtually resurrect the MEGS-A instrument and fill the observational gap left by the MEGS-A failure, thereby improving spectral irradiance prediction. The current AIA data stream on the left is transformed into a virtual measure of UV. On the right, the SDO-ML product. The team demonstrated that with 4 years worth of cotemporal SDA AIA and SDO Eve MEGS-A data, they were able to create a virtual MEGS-A that would be available as long as AIA is functioning, and achieving a median error of 1.6% across MEGS-A lines, outperforming a number of approaches, including a differential emission measure-based approach. Well, can we use AI to understand the sun's influence on orbital drag now that we have SDO ML-ready spectral irradiance? We can use data fusion and ML to produce a thermospheric density model to establish solar drag that outperforms state-of-the-art. Machine learning techniques can leverage solar data to construct thermospheric density models, both in accuracy and computational speed, while also providing uncertainty estimates of the predicted quantities. The team used machine learning and solar activity data to improve orbital drag estimation, basically, and a comparison of this thermospheric density model between the solar drag and an NRL model shows significant benefit. In this challenge, the team integrated solar data, geomag data, and ionospheric data to predict something that affects our daily life, daily technology, like disruption of GNSS, GPS. The complex nonlinear nature of Sun-Earth interaction makes predicting space weather effects difficult. To date, physics-based models do not make predictions on useful spatial and temporal scales. The same physics that leads to fluctuations in ionospheric electron density that causes scintillations, which creates disruption in GNSS, GPS, also manifest themselves as the aurora. By fusing solar magnetospheric ionospheric data with auroral imagery, this ML pipeline significantly improved predictability of GPS GNSS signal disruptions and achieved 15% improvement over the state-of-the-art predictions, and developed custom architecture to predict 1 hour into the future. Now, can we forecast ground magnetic perturbation measurements given changing conditions in the solar wind. The team developed a deep learning model which summarizes 2 hours of solar wind measurements and forecasts geomagnetic perturbation for the northern hemisphere with a lead time of 30 minutes. The scheme outperforms relevant baseline models with a mean absolute error of approximately 60 nanotesla and a probability of detection of approximately 80% across all stations. This polar view shows the supermag ground baseline left and the ML results to the right. This is the newest spacecraft in Heliophysics fleet, Parker Solar Probe, going to a place where no spacecraft has gone before, really sampling the solar wind and thereby trying to uncover the origin of the solar wind. The question was, can AI help us find the complex structures in the solar wind? ML can learn to find, organize, and classify complex structures in the solar wind to advance our understanding of the fundamental building blocks that make up the magnetic field of the solar wind at different points in space. Identifying complex layered structures in the solar wind is an enormous pattern recognition task. For example, the top panel shows from left to right interplanetary coronal mass ejections, force detection 1971, interplanetary magnetic field enhancement, force detection 1983, switchback, force detection 2019 with Parker Solar Probe. What next? The pipeline is able to identify distinctive features and group similar series into recognizable patterns using only 3 million operations instead of the 90 trillion from the traditional approaches. The findings revealed multiple clusters of solar magnetic field structures. What can we learn about heliophysics from other stars? Telescopes like Kepler and TESS measure brightness over time on single pixels for stars light years away. ML can learn from faint star light observations to explain luminosity dips through competing plausible hypotheses in terms of extrasolar transits, spot formation, and the rotational characteristics of each star. The pipeline Starry Spotter transforms Kepler light curves into images, stacks them, and applies computer vision to extract star spots properties. As such, Frontier Development Lab, in partnership with Heliophysics Division, has demonstrated how structured interdisciplinary problem solving, radical collaboration methods, and partnering with commercial organizations with relevant expertise can be useful to NASA science and technology goals. The SETI Institute, in partnership with Trillium, facilitates public-private partnership by acting as a hub between space agency, academic, and commercial partners. And our commercial partners for many of these topics has been Google with significant contribution, IBM, Intel, NVIDIA, and others. Thank you.